Capital Gate Tower. As you can see from the exterior, the Capital Gate Tower was never an easy building to build. The inclination of this building was one of the biggest issues in the construction of the building, but besides this inclination, the building had a fatal problem to be solved: the twisting of the building. In our last week's presentation, we talked about the external diagram, which is a skeleton work for a twisted look. This diagram is a splendid foundation that can realize the twisting exterior of Capital Gate Tower. It was very hard and challenging construction, not even for the experienced constructors. But after this massive process, to realize twisting building, there remained the last piece of puzzle to realize twisted facade. Facade means that exterior of building that is closed by glasses. To make twisting facade, they simply could use curved glasses itself, but it is very expensive. So they used triangle's unique principle to make it look twisted. Triangular foam glasses can pivot 3 directions. Also, they are connected with adjacent glass panes. It means that with making connection angle between glasses different, they can make every angle of facade differently. By this, they can make various complex geometric surfaces. With this principle, they could make iconic twisting facade with a shorter budget. Even with this relatively cheap method, it was still a highly expensive project of a budget of $35 million. Consisting numerous amounts of glass panels, you can see that many different diamond units organize the twisting facade. This diamond unit consists of 18 glass panes, and to make twisting facade, 728 diamond unit was needed. It means there are total about 26,000 triangular panes, weighing 46 million pounds and about 2 times more than the total steel used in the building. Problems occurs at this point. It consists of massive amount of glasses, and because it can be broken easily than other materials, they had to supply a large amount of glasses safely. The team was under constant stress to deliver numerous glass to the site. Delivery process was as follows. The steel framing was manufactured in Austria, and the glass was produced at the Special Glass Company in Wisconsin, USA. This was where the glass was processed and cut. The frames and glass made in each country were delivered to Musafa in UAE. This city was very close to the construction site, had high access to the port, and at the same time, there was a glass industrial factory. Now, the glass and frames were combined here, and finally, a diamond-shaped window was made. The delivery required the closure of 3 lanes of the northbound coast road motorway running from Musafa to Abu Dhabi with police escort. This was such an important job and required high caution. Now that the glass panels have safely arrived to site, it was their job to finally arrange the glass facade. However, Capital Gate Tower has no ordinary glass skin. These glass cladding had to be ensured that it would fit in the perfect position, and more than that, they had to be able to accommodate massive movement compared to normal skyscraper. We have mentioned before that the Capital Gate Tower's precambered core strengthens as it grows, so it means that the skyscraper will not stop moving until after completion. Even more than that, The tower also had to embrace the Abu Dhabi's difficult climate conditions like temperature and wind. The average annual temperature is 26.8 degrees. Abu Dhabi, it reaches over 50 degrees Celsius in summer. In wind, sandstorms usually blowing and the average wind speed is 14.1 kilometers. Keeping these climate environments in consideration, the construction team had to find reasonable solutions to realize this complex facade with glass panels. It should have a capacity to accommodate additional movement caused by wind and temperature changes which would expand or contract all the steel beams and glass panels. Everything was pre-calculated through the 3D model, but to stop the glass shattering and keep the building watertight, the panels had to be designed to shift by up to 20 millimeters. Such a scale was never heard of in the normal skyscraper rulebook. Any accident will cause the whole of the glass panel to be removed. With glass installation ongoing, the manager needed to know the panels will successfully perform. Hence, a pre-test was necessary. The test, which was carried out in the Dubai laboratory, involved the simulation of worst weather case scenario. Plane engines and many liters of water were used to simulate worst case scenario to test the glasses to the limit. The glasses had to pass several tests to prove it's up to the job, and when confirmed, they were able to hold it up to its position. The first time they had a full water test, they had a leak. Water had flown inside and penetrated the inner seal. If it was a fundamental failure, they had to go back to the design step, so the cost and the budget and the program will all go completely out the window. Luckily, it wasn't a design failure. The drainage tube had been blocked with sand. Removing it, the construction could proceed. Even with a small risk as this, it could cause devastating results in the future, and thanks to these tests, they were able to have precaution. With this difficult building, however, one problem is solved, the other is just around the corner. How did they cope with this unpredictable extra movement? Normally, as a diamond-shaped unit has 4 vertex points, it would be reasonable to fix all 4 points. Each point meet with 3 other diamonds, and so in total, each node gets fastened 4 times connected with each other. However, capital gates each large panel was fixed in just 2 places at each side. A special sliding joint was developed to locate it at the top and bottom of each panel and allowing space for additional vertical building movement. As the diamonds were stacked over one another, starting from the bottom, the remaining unfixed 2 points would be fixed by attaching the next diamond, and this process would repeat. This special system made the glass facade capable of not only resisting vertical loss due to the changing core, but it would help resist the strong winds and also give room to keep the water out. The minimal number of fixings means steel was used for the cladding frame rather than the more usual aluminum, which would save the budget. It was an almost perfect solution. However, there had to be even greater care to ensure there was no accident until the construction was completed. They used a special system in connecting the diamonds too. Diamond connects to each other by a two-layer bespoke seal. Flexible spongy seal allows the facilitation of movement and keeps the water out. But if any water does seep through the outer seal, drainage tubes fitted at intervals let the water flow out to prevent molds growing and water damaging the structures. There was the issue of thermal movement. When the temperature could reach 50 degrees in the summer, diagrams that already installed were changed by temperature. Craig Looney, who was construction manager, said at 10 in the morning, when you were about to install a panel, you didn't know where to put it. You could find a panel that didn't fit one day would fit the next day. This delayed the construction schedule. But the team lifted and installed panels using cranes and their hands many times. It seems unproductive, but they started using flat steel and glass to make twisted facade. So this method was not a big deal to build a tower. Finally, they could manage to get the structure and cladding completed for the November Grand Fix. This week, we talked about focusing on the glass that consists of capital gauge facade, including making and installation of glass facade. Next week, we will talk about hollow core and cantilever splash.